We were talking about the transmission line parameters chapter. We went through some of the preliminary stuff at the beginning, and then I think we stopped at insulators. We did not start insulators. So we mentioned that the workhorse of the transmission line conductoring industry is what? The ACSR conductor. It's the aluminum conductor, steel reinforced, which has a steel core and these aluminum electrical conducting strings around it. Yeah. So there's strands of aluminum, strands of steel around them, strands of conducting material. And the steel is to give you the reinforcement or the strength required to prevent conductor sagging, which is a major consideration. So it's a new word that we did not use before, but sag refers to the distance between the conductor and ground. Okay, so this has to be a minimum clearance. There's a minimum requirement depending on the voltage level, of course. If the voltage level is low, you can go lower. If the voltage level is high, you cannot go below a certain level, right? Otherwise, somebody passing by down here will get electrocuted, and you do not want that to happen yet. So this is what, I mean, the steel core is what gives you the strength. And if you have, the stronger you have, the stronger this, or the more steel you have, obviously, the more, okay, this is called, so we said that this is called sag, right? And then this is called span, right? So this is called the span between two towers. So obviously you would like to keep the span as big as possible, right? Because you want to minimize the number of towers because it's a cost, right? And it's not just a cost, it's also a visual effect that you do not want to see, and you have to have roads leading to the tower, etc., etc. So you want to maximize the span, and you would like to make sure you maintain a minimum sag. And to do that, you have to have strength for this conductor, right? This conductor should be able to maintain certain stiffness, and that's what the steel buys you. So the more steel you have, the bigger the span, obviously, that you can have, but for the same amount of current carrying capacity, you'll have a bigger conductor because you have more aluminum strands that you will require in that case. So which means a bigger tower, right? Heavier conductor, bigger tower. So it's a big optimization problem. How many towers do you want to have? What's the weight of the conductor? What are the wind speeds? Again, these conductors have to make sure to withstand wind forces that are going to be swaying the conductors back and forth. So hence the requirement for the steel core. Again, even though this is the workhorse of the industry, and I would say 99% of the transmission line conductors are all ACSR, many people are working on different alloys. So the idea is to give strength to the aluminum while maintaining a low resistivity, right? So people work on different alloys of aluminum so that they can minimize the amount of steel that is used by using a heavier or better strength aluminum, right? So they've come up with different kinds of conductors. I talked about, briefly about superconducting materials, and people are working on high temperature conductors. They're basically all alloys of aluminum, right? We're not chemists. I mean, it's not something, and this is not an electrical materials class. I think you study electrical materials in 322, right? So 320, 370. So people are working. I mean, the electrical people, especially the power people, they tend to work a lot on materials. Especially when they're talking about the people related to high voltage engineering. So the high voltage engineering people get deep into the materials aspect of. So I took a course on electrical materials, not the semiconducting materials that you study in 370. More on the insulating materials that we use in cables, etc. In cables and insulators, etc., etc. So we do not teach a class like that here, but I mean, this is a lot of what the high voltage people study. Insulators. We said that insulators are used to, to hang or carry the transmission line conductors and insulate between the conductor and the tower, right, which is typically grounded. So, and you have typically strings of insulators, and these insulators are typically made of porcelain or toughened glass or polymers, right? So polymers are lighter weight, porcelain are heavier weight. These are easier. The polymers are more difficult to break. The porcelain and toughened glass are easier to break. So, but again, it's maybe they're for polymer insulators you would need a longer string. Their insulating characteristic is not as good as porcelain conductor. But again, that's what people are working on, changing the shape. So they typically stack many of those on top of each other. So in the next slide, I show how many they stack on top of each other for a certain voltage. Again, we do not have to do this calculation, and that's what we've studied in a high voltage engineering class, but there are typical values. For example, in this table, they show you that for 69 kilovolts, you typically don't bundle the conductors. You remember we talked about conductor bundles, so instead of a single conductor carrying the phase, you create bundles of conductors to carry the phase current. Why? Because you want to prevent mainly corona, right? And for current carrying capacity, but mainly for corona purposes. Yeah. Why? Because when we look at the electric field calculation around the conductor, we will see that electric field, basically the vector of electric field is radially outwards from the conductor. You put two conductors next to each other, and the electric field around the conductor, they will sum up and they will decrease in the vicinity of the conductor. Hence, ionization of the air around the conductor can be decreased, which is what is called the corona effect that we mentioned last time. So bundled conductors are typically used at higher voltages. So here at 765 kilovolts, you typically use 4 conductors per bundle, for example. And then cross-section of the conductor, bundle spacing, they talk a little bit about those. But here, this is the number of strings, number of standard insulator discs here. So this is the number of standard insulator discs that you would use, for example, at 69 kilovolt versus 765 kilovolts. So you can see I use 30 to 35 of these discs stacked on top of each other, hanging from the tower to carry the conductor when it's at higher voltage, right? So it's just the insulating capability, right? The path between the conductor and the tower is insulated by these insulators, and the more tortuous you make this path for electrical current to pass through or to conduct, then the better insulating capability you have, basically. So we will not study the design of these insulators, and we will not get deeper into this. I just want to introduce the concept of insulators. You would study this in a high voltage engineering course, the design of insulators, selection of number. But the idea is, okay, the higher the voltage, the more the insulators you have to use. It makes sense, right? The bigger the distance that you need to. What else? The shield wires, we talked a little bit about the shield wires. So there are wires on top of the tower. So in addition to the 3-phase wires that we have, there are wires on top of the tower that are typically for lightning protection. They're typically used for lightning. So it's the tower would have the insulators, 3-phase wires hanging here, and then there would be a shield wire on top between the towers as well, right? So this will also be connected between the various towers. The shield wire up here, and you do not use one shield wire continuous. It's not like the phase insulators. You typically you put shield wires above a few 2-3 towers because you do not want to have a big resistance between the place where lightning strikes and the grounded connection. So you would put shield wire, across 2-3 towers and then ground, 2-3 towers and ground, right? So it's not something continuous like the phase conductors. So they're also made of either because they don't carry current for a long period of time, right? Then you don't need really. Again, the electrical equipment is typically rated for for 2 things, right? Either heat dissipation limit, and a physical phenomena, physical property. Physical phenomena would be in the case of conductors next to each other. It's the insulation between the conductors, right? But here the conductors are up in the air, right? So we're not worried too much about the insulation between conductors. We're worried about the insulation between the conductor and the tower. So we use these insulators. But the objective of the shield wire is to bring that lightning current from where the point it strikes to the ground as fast as possible. Yeah. So these conductors would be, they don't have to carry current for a long period of time, right? So they can be thinner, smaller wires. So they can sometimes be high-strength steel, or sometimes ACSR, but with much smaller cross-section. The idea is they are much smaller cross-section, lighter wires that are used to bring the lightning current from the point where it strikes all the way to ground. So that's the objective of these shield wires. And we said that they would be grounded to the tower, so they would, physically they would be connected to the ground at a tower, every few towers where this ground connection is happening. Yeah. And you would have to design the ground connection properly. Again, we talked briefly about that, and this is something we don't dwell into here in this class, but again, grounding design is a big topic in power engineering as well. So it's you want to make sure that the resistance between the point where the lightning strikes and the ground potential is as low resistance as possible. So there's techniques to design grounding mats and how to maintain the ground connection. Did anybody look at the grounding electrode outside the batil? You saw it? Okay, that's good. So you believe me now? Okay, so we talked about many factors related to electrical transmission lines. So there are electrical design factors. So the obvious electrical design factors are the losses across the transmission line, which affect the thermal capacity. So we talked, we will talk more about those and how to calculate these losses. But again, the conductors have a resistivity. This resistivity means there's an I squared R loss associated with that. So you have to make sure you don't exceed the thermal capacity, because the more you heat the conductor, the more it expands. If it expands, it will sag, right? So sag is the distance between the ground and the conductor. You do not want this distance to exceed a certain limit, right? You want to make sure that there's enough distance between the ground and the conductor. So you cannot overheat these conductors. They will not burn. They will not burn, but they will sag. They will expand more. So there's a limit on thermal capacity. And of course, there's a limit on spacing, because you have to insulate the conductors from each other. So phase A, phase B, and phase C need to be a certain distance away from each other. What else? Series impedance affect line voltage for certain conductors. And of course, there is the effect of the shunt capacitance that we briefly mentioned. So the capacitance is due to the fact that these conductors carry a charge, and they are separated from the tower, which is carrying ground potential, right? So you have two basically points in space that have different voltage potential and an insulating medium, or dielectric medium between them, right? Which is a big capacitance here. So this big capacitance, basically, again, it's from an electrical circuit perspective, this capacitance, as soon as you connect it to a voltage, has to be charged. So there are line charging currents associated with charging these capacitors here. So these line charging currents associated with these capacitors are leading in power factor, right? So sometimes you actually have to, and we talked about leading power factor and how it affects the voltage of the power system, right? So leading power factor refers to positive reactive power being pumped into the system. Positive reactive power being pumped into the system leads to voltage changes or voltage rises in the system. So sometimes you actually have to put shunt inductors on lines, especially when they are lightly loaded, right? So these lines that are lightly loaded have these capacitances because of the fact that you have this conductor hanging in space between it and ground. So you have a capacitance that is physically there. So sometimes you have to add an inductor actually in a power system to be able to counteract the effect of these positive reactive power, or elements that are injecting reactive power into the system, causing overvoltages. Line insulation, we talked about insulator discs, shield wires, line height. So these are all electrical factors that affect transmission line design. Mechanical design factors are many as well. Conductors that need to be strong enough, the suspension insulator strings. Again, so not just the conductor needs to be strong, the insulator stack itself needs to be strong enough to be able to carry it. And we said that these insulators, if the strength of the conductor and the insulating material and the insulator stack will sort of define the span between the towers. So So it's very important to be able to select and optimize the span of the tower and select proper conductors and insulators. Yeah. You also typically find when you're driving by transmission towers, has anybody noticed when you drive by transmission towers, you find sometimes these balls or things between things in the line that look like a dog bone, like a something like a ball. The balls are very clear, right? Because you typically the dog bone dampers are less evident to you, but you will see sometimes that you will have these dampers that hang on the insulators as well. So these balls and these weird looking dog bone dampers, they are vibration dampers, right? So vibration will cause this line to oscillate, and it can be due to wind or mainly wind here. So you would add these vibration dampers along the line to be able to make sure that you do not resonate or you do not vibrate the line at its mechanical resonance frequency. Otherwise, it will not be damped, right? Anything that is vibrating or oscillating at its resonance frequency will not be damped. Like an electrical circuit, if you provide it with current at its resonance frequency, then the impedance will basically be decreased considerably, right? If you provide it at a voltage at its resonance frequency, and then the capacitance and inductance effects will completely be eliminated, and you just have the resistance effect, which is small in a power system, which means you will have large currents, right? So mechanically, it's the same. There's a resonance frequency for the line. For any mechanical device, if you resonate or move or vibrate the line at its resonance frequency, the vibrations will not be damped. They will be underdamped, and this line can be vibrating even more, right? So we add these vibration dampers along the line. Again, environmental factors, we talked about those a little bit as well, because again, you have to have a road leading to these places, to these transmission towers. These transmission towers are going to be close to people, so you have to make sure that they're okay with seeing this. There's a cost of land effect, of course. If you don't want to buy a big piece of land for millions of dollars, and then have the utility company come put the transmission line right through your land, right? So they will take a small right of way, pay you some money for it, but the land price around the transmission tower will not be as good as land price away from the transmission tower, right? So for obvious reasons, visual effects, people worried about the electromagnetic effects of the transmission tower or the biological effects of the transmission tower on humans. So there is a lot of design, economic and environmental considerations that go along with transmission tower design. So that's a lot of discussions that we talked about. So let's go back and go to our core, which is what? The core, or what we're trying to do with this chapter, is figure out how to calculate the R, Jx, and Jb over 2. Right? We want to calculate R, X, and B. I mean, this is our objective from this chapter, really. So that's what we'll do now, right? So it's all stuff you've studied before. So we will not spend too much time or dwell on it. But again, we know that the resistivity or the resistance of a conductor depends on its resistivity at a certain temperature, multiplied by length, divided by the cross-section area of the conductor. So, and it's a direct substitution. I mean, the resistivity of a certain material is something you would calculate. I mean, it's you typically extract that from certain tables, and this is at a specific temperature. So this is resistivity at 20 degrees C, for example, for various types of conductor materials in different units. And then this is the temperature constant that we will use in the next equation when we have the conductor operating at a different frequency. And this is DC. This is DC resistance. AC resistance is a bit higher than DC resistance because of what? Why? What is that called? Yeah, it's called skin effect. So skin effect is, okay, let me draw something quickly. So if you have a conductor with AC current flowing through it, you will have, again, conductor with AC current means you have a magnetic field, right? This magnetic field will be around the conductor using the right-hand rule. And then if you have a time-varying magnetic field, and you have an electrically conducting material in that magnetic field. If this conductor is obviously electrically conducting, right? If you have an electrically conducting material in this magnetic field, what will that do? It will induce eddy currents in the material, right? So you have a magnetic field due to this current, that is this magnetic field around the conductor, and this magnetic field around the conductor induces eddy current loops in the conductor. Sorry. These eddy currents will be typically opposing the current that originally created the magnetic field. So what happens is, if you look at the sum of the currents in this conductor's cross-section area, you will see that these eddy currents are going this way, and then this main current is going this way. So what happens in the center of the conductor is that there's a decrease in current density in the center of the conductor, right? So there's a decrease in the current density in the center of the conductor, and there's a corresponding increase. So this, then at this surface of the conductor, there's a, the conductor, there's currents that are opposing it in the center, but there's nothing opposing it on the skin of the conductor, right? So that's sort of the summary. That's basically what happens due to skin effect. So its currents in the middle are sort of opposing this main current and pushing it to the outside. So when you push it to the outside, this current is flowing in a smaller cross-section area, right? We said that if current is flowing in a smaller cross-section area, that means the resistance will do what? They're inversely proportional. The resistance and cross-section area are inversely proportional here. So which means that the resistance will increase due to skin effect, right? So you're pushing the current to only move on the outside of the conductor, meaning you will cause an increase in the resistance. So the table, we have a table in Appendix A3, I think. I think it includes, this is from your textbook. Yeah. So these are different conductor cross-sectional area, size of conductors. In circular mills, it's a unit that they use. And then if you look at, DC resistance versus 25 hertz resistance versus 50 hertz resistance versus 60 hertz resistance, we see that there's a slight increase due to the fact that you have skin effect acting on a conductor here. Okay, not very significant, but there is a certain percentage. I think 1% between DC, 1 to 1.5% between DC and 60 hertz. So it's something you have to account for. Yeah. So it's in the table. Again, you're not going to be calculating this for standard conductors that we use. Yeah. Okay. Okay. So after you calculate the DC resistance, there's an effect for spiraling, right? So we have these strands, these aluminum strands are wound around the steel cores, right? So if they are straight, they have a certain length. But because you're winding them around the steel core, they're also greater in length than the cross-section, than the length of the conductor itself as well, right? So this also accounts for an extra 1 to 2% increase in resistance. Temperature, of course, accounts for increase in resistance as well. So you will change the resistivity based on temperature, and this T is from this table. This temperature constant T is from this table. So for annealed copper conductor, the T is 234.5 degrees C. So this is the T that you would plug here, and this is the temperature, that original temperature. So this is original resistivity at T1, and this is, which is, for example, you will get that from this table. For example, this is resistivity at 20 degrees Celsius. So T1 would be 20 degrees Celsius. T2 would be maybe 50 degrees Celsius, for example, and you will use the temperature constant when the temperature changes, right? So for every material, there's a certain temperature constant when you need to calculate the resistivity at a different temperature. Yeah. So that's this T here, and there's an example in the slides. Yeah. Again, we talked about skin effect. So the AC resistance or effective resistance of conductor is a little bit higher. And of course, you can calculate that more exactly from the AC current flowing. This is the RMS value for the AC current, for example. And if you know the exact losses, then from the losses and the AC current RMS value, you should be able to calculate the value of the resistance here. Or you extract that from the tables, right? So from the tables that you have, you can also extract that, yeah. We will not talk about magnetic conductors, since it's not something we are interested in. So let's look at an example. So this is an example of a stranded conductor, and they want you to calculate the DC and the AC resistance. So they tell you from table 8.3, list a conductor for 0. This is the conductor that they list. So these are all several 40 type conductors. This is the gauge, or the sort of the size. American AWG stands for American wire gauge. Okay, so this is it's called conductor 40. Let's see which one of them. So conductor 40 with 12. It's a copper conductor with 12 strands, and the strand diameter is 0.3373 centimeter or 0.1328 inches. Let's see which one that is. 0.1328. Yeah, so this one is 0.1328. The diameter of the individual strand in inches. So they're talking about this conductor here. They give us the diameter, they give us the breaking strength of the conductor, they give us the weight, approximate current carrying capacity, the geometric mean radius at 60 Hertz. And geometric mean radius, I mean, again, this conductor, if it's solid, you know the radius, right? It's easy. If it's a copper conductor that is solid, you will know the radius. But if the conductor is not solid, it's these, and it's stranded, and it has a steel core in the middle. So it has an effective radius corresponding to this size, right? So this radius is called the geometric mean radius. Okay, so that's what this means. And then they give you the resistivity. So this is the one. This is the conductor we're talking about. They give you the resistances at DC 50 Hertz, 60 Hertz, at 25 degrees Celsius and 50 degrees Celsius, and they also give you the inductive reactance in ohms as well for the conductor, assuming 1 foot spacing between the conductors. And we will see the effect of spacing between the conductors, and they also give you the shunt capacitance of mega ohms, but I don't know, for some reason it got. I guess mega ohms per mile, I guess, at 1 foot spacing. We'll also look at how to calculate this exactly. So we will calculate the inductance and capacitance as well in this chapter. I just, you can also extract them from tables. That's what I'm saying, assuming that the spacing you use is the same. If the spacing you use is not the same, of course you will have to recalculate the capacitance. Yeah. So this table is in the back of the book, and we will use it to solve some of the homework problems. Yeah. Okay, so verify that the total copper cross-sectional area is so and so. So how would you do that? So if they're giving you the diameter of each strand, and they're telling you that it's copper, so you would, I guess, go to the diameter of the strand and calculate the area and just multiply by the number of strands, right? So strand diameter is 0.3373, which is 0.373 millimeters. So the area, so you calculate the area, so it's pi d squared over 4, and you multiply by 12 to calculate the total conductor area, right? Total copper area. So verify that the DC resistance at 50 degrees C is 0.1876 ohms per kilometer. So they gave us a DC resistance, and they just want us to verify. So let's look at the table to. It's the resistance at 50 degrees Celsius. So this is the this is our conductor, the 0.1328 diameter one. We go here. So it's this conductor, a 0.1328. You go to the side, and the DC resistance is 0.302 at 50 degrees Celsius, 0.302 ohms per mile at 50 degrees Celsius. Yeah. So I guess they want us to verify that. So how would you do that? You just substitute in the equation, but this is at 50 degrees Celsius. It's not at 20 degrees Celsius. So you have to use the equation where this equation here, where you change the temperature, and you have to look at the temperature constant for the specific material. So this material is hard drawn copper, right? So they're using hard drawn copper for this conductor. So if you go to this table here, copper, hard drawn copper, the temperature constant is 241.5. So this is hard drawn copper, temperature constant 241.5. You go back to your equation, and T1 was 20, that's from the table, and this is the resistivity also given from the table, and the new temperature is 50 degrees Celsius, and the temperature constant from the table is 241.5. And we calculated the new resistivity. So now they want to calculate the resistance, I guess, after that, yes. And they considered 2% increase due to spiraling, right? So, how do you calculate resistance? It's rho L over A. Which rho? It's this new rho that you calculated at 50 degrees Celsius, which is this. L is the length of the line, so it's 1 kilometer. And then they added 2% increase because it's a spiraled conductor with a steel core. So, and this was the cross-sectional area that you verified here, right? So just rho L over A calculation. Any questions on this? It's just direct substitution or picking up from the tables. Like the part C is picking up numbers from the table, basically. So part C, from table 8.3, determine the percent increase in resistance at 60 Hertz versus DC. So how do you do that? You go to the table, look at the resistance at 60 Hertz versus the resistance at DC, and look at the percentage increase. So I'm not gonna, any questions on this? I mean, is everybody comfortable? So if I go to the table here, they will give us for this 0.1328 conductor, they will give us the resistance at DC. What temperature? At 50 degrees Celsius, right? So they will give us, for the 0.1328 conductor, where is it? This one. You go and take the DC resistance, 0.302, and 60 Hertz resistance, and 0.303, and you find they're asking for what is the percent increase between DC and 60 Hertz for this specific conductor. Okay? So they just extracted the information from the table and did the ratios. So the DC, they did it at 50 degrees Celsius and 25 degrees. Appendix A3 gives you the data at 25 degrees Celsius and 50 degrees Celsius. So they did it at both, and here you see the percentage increases between 0.3 and 0.7 for 25 and 50 degrees Celsius. So any questions on calculation of resistance? It's either rho L over A, or calculate the new rho by considering the temperature coefficient, and then extracting the information from the appendix A3. Really, it's nothing more than that. So any questions on calculation of resistance? Okay. Okay, so calculation of inductance. So the way we will calculate inductance is the following. So we will start with trying to calculate the flux density. So we'll start with Ampere's law, actually. We'll start with Ampere's law, which tells us, the integral of H dot dl around the closed loop is equal to the current enclosed, right? So knowing from that, we will know the current enclosed because we have a conductor that's carrying current I, for example, right? So we will know what the current enclosed is, and we would like to calculate H, right? So we will calculate H in terms of the conductor dimensions and the material of the conductor. After you calculate H, you will assume a linear relationship between B and H, which is defined by the permeability of the material, right? So we will assume a certain permeability. This conductor is in air, right? So our relative permeability will be 1 because we're in air. If the conductor is underground, the relative permeability will be different, right? You will be given a relative permeability. But the calculations are valid for conductors, transmission lines in the air, or transmission lines underground. So after you calculate, find H from Ampere's law, you will be able to find B from the relationship between B and equals mu H. After you find B is the flux density, right? So after you find the flux density in the material, you take a small section of the material and look at the flux density there, and then integrate over the full area. To do what? To find the flux. This flux links the conductor, right? This flux links the conductor in two areas here, because this is the magnetic field will link the conductor. We're looking at the small, conductors, areas of the conductor. So the magnetic field there will be internal magnetic field to the conductor, and there will be external magnetic field to the conductor, right? So there will be a magnetic field due to magnetic field, or there will be a flux linking certain portions of the conductor due to the magnetic field inside the conductor, and then once you go outside the conductor, the magnetic field is linking the conductor itself, right? Regardless of how far you go, right? So there will be two components of magnetic field that we will have to calculate. So internal and external in the conductor. And then after you calculate this flux density, you'll be able to calculate flux from there, and then from flux you'll be able to calculate the flux linking the conductor. Outside, flux will be the same as the flux linking the conductor because we only have the single conductor. But inside, the amount of flux will link a portion of the conductor, depending on the ratio of the areas between the conductor itself and the area where the current is flowing, right? And this will be a little bit tricky. And then once we go outside, basically the flux linkage is equal to the flux that you've calculated from this equation, this integral here. Right, so let's see how we will do that, and then after you calculate the flux linkage, in the conductor, you will divide that by the current through the conductor. So from there you will be able to calculate the inductance. So we will assume that the relationship between flux linkage and current is a linear relationship. The more current, the more flux linkage that you will have in the conductor. So the constant of linearity, constant that is linking both flux linkage and the current, will be the inductance in this case. So basically, we will calculate. The process will be as follows. We will calculate. Here's the process. So we will calculate the magnetic field intensity H, and then we will calculate the flux density B, and then we will calculate the flux. And if it's a single conductor, if all this flux is linking one conductor, then flux is equal to flux linkage, right? If we have a smaller portion of the conductor that is being linked by a smaller portion of the flux that's surrounding the conductor internally, then the flux linkage will be a little bit less because it's linking a smaller area of the conductor, right? There's magnetic field internal to the conductor, magnetic field external to the conductor. If it's internal to the conductor, it's linking a smaller area of the conductor, right? If it's external to the conductor, it's linking the full conductor, right? So in that case, there's no difference between flux and flux linkage. Or flux linkage is equal to the flux that is outside the conductor. After you calculate the flux linkage, you will divide that by the current, and since we assume the flux linkage and current are linearly proportional, their proportionality gain, or they're linearly proportional by a gain called inductance. That's sort of the process that we will follow. Any questions? So any questions in the process, the calculation process? Okay, so what we will assume a conductor with a radius r and 1 meter length, carrying current I, and we will assume that the conductor is sufficiently long so that the end effects are neglected, and it's non-magnetic, so that mu is equal to mu naught, and it has a uniform current density, so we will neglect skin effect as well, right? So this will be the conductor, and this will be the conductor that we'll look at. So the conductor has length 1 meter, and again, there's current I flowing through it. This current I causes a magnetic field in using the right-hand rule that encompasses either a piece of the conductor, an area of the conductor, or the full conductor if this X is outside. So we have to do this, we will have to calculate the inductance due to either smaller elements of the conductor. At point X, we will calculate the inductance, the H at point X. This X varies from 0, internal to the conductor, to some point in space, any point in space, right? Because again, the magnetic field around the conductor, is it going to decrease in strength as you move further away or not? Right? It will decrease in strength. So the magnetic field around the conductor that is due to the current flowing through the conductor will have a certain value around the conductor. Then it will decrease in strength as you move away. So you would like to calculate the magnetic field around the conductor, starting from the radius to as far away as possible, right? If you calculate that magnetic field around the conductor, then from there, you should be able to calculate, this is magnetic field intensity. From there, you should be able to calculate the density of this magnetic field. This density of the magnetic field corresponds to a certain flux flowing around the conductor. This certain amount of flux is linking the conductor. So after I find the flux linking the conductor, I will divide that by the current, and from there I will calculate the inductance. Right? So that's why we have to calculate H starting from the core of the conductor all the way to outside, because what we will end up with having is we will have many conductors. A transmission tower has 3 of these conductors, correct? So each of these conductors will have a magnetic field around it due to the current flowing through it. So we will have to see the effect of the various conductors on each other as well. They will have an effect, right? Phase A will have a current going through it with a certain magnetic field around it. Phase B will have another current going through it with a certain magnetic field around it. So we want to look at the general case of a conductor with current flowing through it, and we want to be able to calculate the magnetic field any point from the core all the way to as far away as possible, right? And then we do that for 1 conductor, and then for 2 conductors in a single-phase circuit, or 3 conductors for a 3-phase circuit. And we will see that they will affect each other, obviously. So let's go through the process. So again, we will start with Ampere's law, which says that H dot dl is equal to the current enclosed. The current enclosed, if I'm going to look at, again, the magnetic field inside the conductor is due to what? A portion of the current, because I said that I will maintain if I looked at my assumptions, I said that it has uniform current density, right? So this conductor has uniform current density, meaning not all of the current I will go through this cross-section area of the conductor. How much of current I will flow through here? Current I is what is flowing uniformly through this conductor with radius r. So current Ix, a portion of that current, is what is flowing through a circle at radius x from the center of the conductor, right? And because we said that the current density is uniform, then the relationship between the current I, total current I, and the current that's flowing in a smaller area of the conductor, the relationship between them is the ratio of the areas. Only because I said that the current density is uniform. So the current is distributed uniformly across the area, right? So if I take a smaller area, then the ratio between the currents I and Ix is the ratio between the areas. Okay, so that's something I wanted to mention. So H.dl is equal to I enclosed. If I'm looking at internal, inside the conductor, I enclosed is going to be equal to Ix. Anytime x is greater than the radius r, what is I enclosed? It's I total, right? So anytime x is greater than r, then Ix is going to be equal to I, right? That's why I split this into two. I calculate the h of x, or the magnetic field strength, inside the conductor first, because the fact that the current that is causing this magnetic field strength inside the conductor will vary depending on the area, right? Depending on this area of, or the radius of x that I have. And then once I go outside the conductor, this I enclosed will be I, right? So that's why I calculate to determine the we split it into two, determine the internal inductance, because of the fact that the magnetic field strength will vary and the I enclosed will vary internally. Once you go outside, it's not, the I enclosed is equal to I, so we will do inside and then outside. Okay, so that we so h of x dot dl is equal to I enclosed. The length of the path dl is this perimeter 2 pi x, right? So h of x times 2 pi x is equal to Ix. So we calculate h of x, which is the magnetic field strength, hx, at a radius x from the core of the conductor. From there, I do what? I said that this Ix is related to I by the ratio of the area. The area is what? 2 pi r squared, right? Pi x squared to pi r squared. So the ratio of the external area is pi r squared. The ratio of the internal area is pi x squared. So the relationship between Ix, which is a portion of I, is going to be the ratio of the areas, or the area where the conductor current Ix is flowing, versus the total area which carries full conductor current I. Right? So if x is equal to r, then Ix equals to I. Right? So the Ix is equal to the ratio of x over r squared. So this is, it's pi x squared over pi r squared, right? But pi goes away with pi. So anyway, so then I substitute, instead of Ix, I write the equation in terms of I, because I will later add this to the inductance due to the external effect, which will carry the full conductor current. So I wanted to find the relationship between them here. So I substitute with Ix here is equal to I, and I rewrite h of x. So obviously the x squared, one of the x squareds will cancel with the x at the bottom, and I'm left with the r squared in the denominator, right? So x squared over r squared times I put it here, x on the top cancels with x on the bottom, and I'm left with r squared in the denominator and an x in the numerator. Yes, sir?
Normally, is I, it should be bigger than Ix, right? The normal.
Yeah.
But this relation, I think, gives a lower I than Ix.
Why?
It's at x over r. X is lower than.
Sure, x is lower than r. So Ix is, so this, I mean, x lower than r, then this ratio is smaller than 1. So Ix is always smaller, less. Right? So this is h of x. So what's the next step? So this is the magnetic field strength at the radius x. And then what? After you know the magnetic field strength, I want to find, my objective is to find the flux linking this portion of the conductor. Right? So after you find the magnetic field strength, I will find the flux density from the relationship B equals mu h. Right? After you find the flux density, you can find flux by integrating the flux density over the area, right? Or from the relationship B equals phi over A, right? So we will do that. And then we look at, is this flux linking a turn, or is it linking the conductor, the full conductor, or is it linking an area portion of the conductor, a smaller area of the conductor with relationship to the larger area of the conductor? In this case, it's linking a smaller area of the conductor. So we have to, in this case, the relationship between flux linkage and the flux that we've calculated will also contain this ratio of the areas that we talked about, right? So, and we said that this conductor is in air, right? So the relation between the flux density and magnetic field intensity is mu naught. We said that relative permeability is 1. Sorry, we'll assume this relative. It's an assumption that we assumed here. The relative permeability is equal to 1. I think we said that somewhere. Yeah, 2. It's a non-magnetic material, so it's like air. So it's the relative permeability will equal to 1. So then B is equal to mu naught h of x. So you just take this h of x that you have here, multiply it by mu naught. And then you do what? We want to calculate the total flux that is in a certain cross-sectional area of the conductor. So we know that the relationship between flux and flux density that we've calculated is defined by the integral of the flux density over the full area. So if you have the flux density, which is the number of flux lines per unit area, and then this area is basically defined by what? It's dx because I have a length of 1. So the area that the flux is cutting is this distance dx, right? If this radius is x, then this distance is a portion in the same direction as the radius, right? So it's a distance dx, right? So this distance here that the flux is cutting is dx. The length is 1, right? The length is 1. That's why I have here a dx. I don't have something else, right? So this is an area really, right? Because we said that I calculated the magnetic field density. I would like to calculate the number of flux lines, right? So this is the magnetic field density that is at a certain point x away from the center of the conductor. This magnetic field density is in an area. I would like to calculate the total number of flux lines passing through that area. This area has a width dx and a length 1 meter. So this 1 meter is what you have here, basically. This is area, basically, right? So any questions about this? So if I would like to calculate the number of total flux, I would have to perform this integration, basically. Before I perform this equation, before I perform this integration, I also need to look at, is this flux linking the full conductor, or is this flux linking an area or a smaller portion of the conductor? Since I'm talking about internal, so this x here is still internal to the conductor, right? It's linking what? It's not linking this full conductor outside. It's linking this portion of the conductor that's less than at a radius less than r. So the flux lines here are linking only this portion of the conductor, right? They're not linking the external area of the conductor. So there's a ratio between the total flux linkage that is linking this area versus the total flux that is calculated by this h of x that I have here. So the relationship between flux linkage and flux, right? So I calculated the total flux, right? If I calculate the total flux, this total flux is linking a smaller area of the conductor. It's not linking the full conductor. So the smaller area of the conductor versus the full conductor, the ratio between them, or the relationship between them, is the area as well of the conductors. So the differential flux linkage is given only for x over r squared of the total current, right? It's only linking part of the turn, part of the conductor. This part of the conductor is carrying part of the current, right? And this part of the current versus the full amount of current, the relationship between them is this area, the ratio between the areas. So the ratio, or the relationship between the total flux and the flux linkage is also the area, right? So I took my b of x here, and plugged it in here, and I multiplied by the x squared over r squared here, so to calculate the flux linkage. So then I will, this is an equation in terms of x, my unknown is x here, so I will integrate, I would like to calculate the flux linkage from the center of the conductor all the way to its radius, right? Everything that's linking the conductor from the center to the radius x equals r. So I will calculate flux linkage from 0, which is the center of the conductor, to radius r. I want to calculate the flux linkage. So I will take the flux linkage that I just derived and do this integration. I end up with 1 over 2 half times 10 to the minus 7 times I. And then I know that the relationship between the relationship between lambda and flux linkage is the inductance, L, right? Where is this coming from, guys? So if you would like to, L is equal to, or VL is equal to L di by dt, right? I of L is equal to 1 over L integral of v dt. This integral of v dt is the energy that basically you've placed voltage across an inductor, right? If you assume that this voltage that you placed across an inductor looks like this. This is VL. This is voltage that you placed across an inductor. When you place voltage across an inductor, what happens? Flux builds up around the inductor, right? If you place a voltage, current will flow through the inductor coils, and then flux will build up around the inductor, right? This flux is actually linking, or it's called flux linkage, right? This flux is linking the inductor turns. What is this how do you calculate this flux linkage? This flux linkage is actually this. So this integral of voltage, E equals, remember this equation, A equals n d phi by dt? Integration, so bring this dt by here. Bring this dt, so E dt. This is voltage, right? So integration of voltage is equal to n, so it's the number of turns, multiply by the flux. So if you integrate here, what do I get? I get that the number of turns multiplied by the flux is equal to the flux linkage, right? This is, the integration of voltage is the flux linkage, because it's the number of turns that are linked by the flux, right? It's the number of turns that are linked by the flux. That is called flux linkage. So what is this flux linkage? This flux linkage is actually the integration of the voltage across each of these turns. So I have an inductor here, which is a certain number of turns. I've placed a certain voltage across it. This voltage has to have an average value of 0. Remember, in inductor, again, you cannot keep adding, it's like a capacitor. You cannot keep charging a capacitor, right? You will charge a capacitor, then discharge a capacitor. Because if you keep charging a capacitor, what happens? The voltage keeps rising, right? You cannot keep the voltage rising because this dielectric will have a breakdown strength. So you cannot break the dielectric strength. So what you do with capacitors is you charge them and discharge them, charge them and discharge them, if you would like to maintain a certain voltage. Same thing with inductors. Inductors help you maintain a certain current. How do you maintain a certain current? You charge the inductors or place voltage across the inductors, and what will happen is flux will build up around the inductor. That's this in this cycle. And then you would like to, again, you cannot keep adding, you cannot maintain that voltage forever, because if you maintain that voltage forever, what will happen? You're integrating the voltage. Flux linkage is the integration of the voltage, right? So you keep this number will keep increasing. If this number keeps increasing, what happens? If this number keeps increasing and the number of turns is fixed, that means the flux keeps increasing. Flux keeps increasing. This is a certain material. The material has a certain flux density, right? After a certain number of flux lines per unit area, this material is useless. You're putting more current, or you have a voltage that it's causing current to flow, and you're not increasing the flux anymore, right? So it's exactly like the capacitor, right? So there's a limit on there's a limit on the value of this integral, right? And that's how you choose the core that you design. The inductor core or the transformer core is based on this limit that you will that they will give you in the data sheet of the material. They will tell you this material has a certain flux density that you should not exceed. Same thing for capacitors. This capacitor has a dielectric strength or a dielectric strength with a certain voltage that it cannot exceed. Right? So we will be able to calculate. So this is flux that we're calculating here. This is flux. Right? This is the flux phi. I would like to calculate the flux linkage. This flux linkage, if I have a one turn, it's 1. I mean, the relationship between, lambda and phi is what? If this is the one conductor, then this n is equal to 1. But now I'm not talking the full conductor, right? I'm talking about an area of the conductor, right? A smaller area of the big conductor. The smaller area of the conductor versus the bigger area, the ratio between them is the two areas, right? So here I calculated B, which is the flux density. I want to calculate phi. The objective is to calculate lambda, right? But I know lambda and phi are linked by the number of turns. Number of turns is either 1 if I'm linking the full conductor, or it's less than 1 if I'm linking a portion of the conductor. This portion of the conductor is a smaller area versus a larger area, so the relationship, this n here, is sort of this x squared over r, x over r all squared. Everybody's okay with this now? So I'm just calculating the relationship between lambda and phi here. And then, what else? So again, VL is equal to L di by dt, and then we said that IL is equal to 1 over L integral of V dt. We said this is now what? Integration of the voltage across the inductor is what? The flux linkage. That's the flux linkage, right? So if I calculate flux linkage, and I have the current, because I know the current's that's flowing through either the small area, which is Ix, or the full conductor, which is I. So if I know lambda and I know IL, inductor current, then I can calculate inductance. The relationship between them is inductance. Okay, that's where this equation on top comes from. It's just from the basic VL equals L di by dt. So any questions on this? Okay, so we calculate the flux linking now, the conductor, the portion of the conductor anywhere between 0 and the full radius of the conductor. So, and at the full radius of the conductor, and we always, at the beginning we substituted, remember we removed Ix and we substituted with regards to, we substituted Ix in terms of I, which is the full current, and the relationship between them was the area as well. So we calculated flux linkage in terms of the current of the conductor. Okay? And from flux linkage, we divide that by current of the conductor to calculate the inductance. This is the inductance due to the internal magnetic field of a conductor. Right? So you have a conductor, and you calculated an inductance due to the magnetic field inside the conductor. And then we want to, again, there's magnetic field around this conductor anywhere in space, right? The value of the magnetic field will decrease with distance, and that's what we saw here, right? The magnetic field intensity. Magnetic field intensity outside the conductor, let's look at the magnetic field intensity outside the conductor, is equal to what? Hx equals I over 2 pi x. So the magnetic field intensity will decrease as x increases, right? So magnetic field outside will decrease as the distance increases. Yeah. So I would like to now calculate the inductance due to the magnetic field outside the conductor. So we calculated the inductance due to the magnetic field inside the conductor. Now we need to look at the magnetic field outside the conductor and calculate the inductance. The total inductance will be the sum of the two of them, right? Because again, it's this inductance is due to the magnetic field internal and external. So it's like two series inductors. which is like two series resistances, you just add them. So what we did was calculate L due to the internal magnetic field. Then we will do the same, exact same process, but we will not have this issue of x over r squared at all. So in here, if we want to look at the magnetic field outside the conductor at the radius x, what we are interested in is from the radius all the way to any point in space, or between any 2 points in space, d1 and d2. So integral of h dot dl is I enclosed. I enclosed in this case is the full conductor current, right? I have I enclosed is equal to I. And h of x, h at the distance x, the I enclosed is 2 pi x, so this perimeter here. And from there I can calculate h of x. After h of x, I calculate B at point x, the flux density at point x. The flux density and h are related by the permeability mu naught. Mu naught is equal to 2 pi times 10 to the minus 7. So bx is equal to 2 times 10 to the minus 7 I over x, right? So then what? After B, the flux density, I would like to calculate what? The flux, right? So I calculated the magnetic field intensity. Then I calculated the flux density. Then I would like to calculate the flux, because my objective is flux linkage. And now flux linkage and flux are the same, because they are both linking the full turn. Right? All this flux outside is linking what? Is linking the same one turn. N is equal to 1 in this case. Before, N was a smaller, the connection between flux linkage and flux was the smaller area versus the larger area. It was only linking an area of the conductor. So it was a ratio of the big area to the small area, or the small area to the big area, sorry. Now flux linkage and flux are the same. So I have my flux density, and I will integrate to calculate my flux linkage. So I will integrate what? I will integrate B of x dx. Again, this dx is dx times 1, right? It's the same. I have the same cross-sectional area. I have the dx times 1. So I will do this integration. I will end up with lambda 1 over lambda 1, 2. In the general case, I want to calculate the inductance due to the magnetic field between any 2 points in space, right? So instead of putting, I can make D1 after that. I can make D1 equal to R, and D2 I can send it to infinity, right? If I just need to calculate a general equation in terms of D1 and D2. So if I calculate this flux linkage between points D1 and D2, I will end up with 2 times 10 to the minus 7 multiplied by the current natural log D2 over D1, right? I can then make D1 equal to radius equal to R, which means I brought this point here, and I can make D2 some point far away, which means I calculated the inductance or the flux linkage from the radius all the way to some point in space D2, right? And we will write it that way here. So, but inductance now due to this flux linkage is this flux linkage divided by the current I. So current I cancels, and I have 2 times 10 to the minus 7 natural log D2 over D1. I think what they do here is what I was just mentioning. D1 is equal to R, and D2 some point in space D. Right? So I end up with the flux linkage equals to the internal flux linkage, right? This was the flux linkage internally, which is what we calculated here, half times 10 to the minus 7, half 10 to the minus 7 times the current. Half times 10 to the minus 7 multiplied by the current, plus the flux linkage due to the external magnetic field, which is 2 times 10 to the minus 7 times the current natural log D2 over D1. 2 times 10 to the minus 7 current natural log D2 over D1. Again, D1 was equal to R, D2 is equal to some point D in space. So this is now the total flux linking conductor P due to the magnetic field inside it and the magnetic field outside it. Is it okay? Clear? Not clear? So if I have now the total flux linking conductor P, I take that divided by what? Divided by I, and I have my inductance, right? We also do They also used some natural log identities. So this half here is equal to 2 times natural log e to the 1/4, and they substituted with that in the equation. So they took the 2 times 10 to the minus 7 as a common factor outside, and then they converted this to they use this identity here to make this natural log e to the 1/4 plus natural log d over 4, and you end up with this term here. And they took this e to the minus 1/4 r, and they call this r prime. So they just simplified. They just did some simplifications, but it's nothing but 0.7788 times the radius of the conductor. So we rewrote this. And then if I would like to find my inductance, it's the flux linkage divided by the current. Which current? The current that created that flux linkage, right? Because now we did it for this one conductor. But now we will bring in another conductor, and we will have current flowing through that, affecting flux linkage in the vicinity of the first conductor. So is everybody okay with this until here? Yes, no? I can repeat it quickly if you... Okay. So let's keep this in mind. This equation is an important equation. This equation tells us what? This equation tells us that the flux linkage due to conductor flux linking conductor P, the total flux linkage conductor P, from where? Internally, from the core of the conductor all the way to a point D. Remember we made this D some point far away in space. So the flux, this equation gives us the value of flux linking conductor P up to a point D in space due to current I carried by the conductor. So how about if I want to calculate the flux linking conductor P due to another conductor? How would I do that? Think of this. This is what? This was flux linking what? Flux linkage between points 1 and 2 in space, right? Points 1 and 2 in space had flux linkage between them due to some conductor carrying current I, right? So I can calculate the flux linking points 1 and 2 due to conductor A carrying IX, due conductor B carrying IY. It will all be the same, but what will change? The current will change, and then the distance between this D1 and D2 is what? The distance between the conductor that's carrying the current, here look at the figure, D1 and D2 are the distance between the conductor that's carrying the current and the point in space that you want. So if I have if I bring in a different conductor here, right? And this conductor is carrying I1. This was carrying I, for example. This is carrying I1. This conductor will carry current. Do you agree that this will also have magnetic field around it? Yes? And this magnetic field will also intersect this conductor, correct? It will intersect this conductor at some point. I mean, this magnetic field at some point will link this conductor here, right? I would like to figure out the total amount of flux linking this conductor. It will be due to what? It will be due to the current it is carrying, which is causing these magnetic fields here, right? And then it will also be due to the flux due to this conductor, which is causing these magnetic fields that are also linking this conductor, right? So we came up with a general equation for flux linkage. We said that flux linkage is equal to what? 2 times 10 to the minus 7, right? Something like that. Yeah, here, 2 times 10 to the minus 7. It was 2 times 10 to the minus 7 natural log 2 times 10 to the minus 7 natural log times the 2 times 10 to the minus 7 I, which is the current that is flowing through that conductor, natural log d2 over d1. So for this conductor, the external flux linkage was equal to 2 times 10 to the minus 7. This was carrying current I, right? I natural log natural log what? d2 over d1. How about for this conductor? For this conductor. Also, what I would like to know what is the effect or the magnetic field or the flux linking points d1, these 2 points, right? I would like to find out what the magnetic field is linking these 2 points. So this is going to equal to what? 2 times 10 to the minus 7 I1 natural log what? Not d2 and d1 anymore. d2 and d1 were for this conductor. Okay, so go back to this equation. This equation says what? That the flux linking points 1 and 2 due to this conductor is equal to 2 times 10 to the minus 7, the current that this conductor is carrying, which was I, right? Natural log the distance d2, d1 away from the core of this specific conductor, right? Now, how about the flux linking also point 1 and 2 due to this conductor? It's equal to what? Forget about what we did here now. Okay, I have d3 and d4 now, right? What is the flux linking points d3 and d4? What is the flux linking point d3 due to a conductor carrying current I1? It's the same, 2 times 10 to the minus 7, but here I1, right? Natural log d3 over d4, right? And then I can bring this d3 and d1 to the surface here, right? In that case, d1 will be the radius of this conductor. How about d3? d3 will be the distance between this conductor and this conductor. And d4 will be